Anton Krumm is a product line manager at the Corning Laser Technologies. Previously, he served many years in the laser and photonics industry in R&D, engineering and technology management. Please join me in giving a warm welcome to Anton. And Anton, you can start with the presentation.
Okay, thank you very much for the introduction. So, and also thanks to the organizer for having the opportunity to talk about laser cutting technology with application examples for automotive and architectural glass products. After a brief company introduction, you will hear I explain the basic principles and also the key benefits of the technology, also in comparison with conventional methods. Then I will come to the application examples for automotive side windows as well for smart windows cutting. We will have a brief look at the environmental impact, and I will conclude with a summary and also to the related available laser platforms for such applications. I think Corning is well known in the glass industry, so I don't spend much time on commenting on our parent company. I rather want to give some brief background information on Corning Laser Technology itself, which was founded in 1995, at that time as Innolage Solutions. At that time already, the company manufactured laser-based machinery for the photovoltaics industry. It was quite pioneering work in the 90s. And in 2012, the company introduced also its laser cutting technology for cutting glass. And no surprise, that caught the attention of Corning. And Corning then acquired the company in 2014. Since then, we continued innovating and with several steps. In the last year, for example, we also introduced a microfabrication platform, mainly for the semiconductor industry, but also, for example, 2 industrial manufacturing platforms for cutting of 3D-shaped glass. I skip this one and come now directly to the principle of operation. As you all know, glass is highly transparent in the visible range, but also in the near infrared. So there's no linear absorption with our laser wavelength in the near infrared. But when we go then to ultra-short pulses and some beam shaping, when we get to such high intensities that we get into the nonlinear regime of the laser material interaction. So, example, we have a typical average power of only 50 watts of the laser, but we have picoseconds, rep rate roughly 100 kilohertz. Then you have peak powers of easily of megawatts, and then high intensities of gigawatts per square centimeter. We do this, so you get out of the laser source, we have the laser beam with a Gaussian intensity profile. With our proprietary beam shaping optics, we transform that beam into very narrow line focus that can be mathematically described by a Bessel function, so that's why it's also called the Bessel beam. And that line focus is of course reaches all throughout the full thickness of the glass. And here you can see essentially that the movement of the laser beam in the glass that it determines the desired cutting contour. So there's no material removal at all. We only, with this high energy or high intensity interaction zone, we modify the material and we weaken it. And the next step, we do the separation process, and we do it such that we follow that nanoperforated contour with the CO2 laser beam, and the absorbed power of that leads then or introduces then a thermomechanical stress profile, which makes then the material cleanly separate along the nanoperforated contour. So the result is then very high quality cuts. It's very precise and accurate cutting. That's why we can do also cutting of freeforms and essentially net shape cutting, as you will see later. There's no taper. There's practically no material loss. The only little debris is essentially because we also have a little bit of chipping, but otherwise there's no material removal. The surface roughness is very low, and we have a very high uniformity. And these are just some examples to illustrate what we can do. Here is a short video clip. That shows just in the rendered video first the principle. You see this is a nanoperforation process, and it's really that you modify the material through the full thickness, and then in the next step we have the separation process, also contactless, of course, and which makes then the separation cleanly along the nanoperforated contour. In the next sequence, you see then how it looks like in the real system. So we bring in the mother sheet on our belt system. Here you see now the process head on our XY gantry, where we do now the nanoperforation. So that means we scribe essentially the contour into the glass, or that we nanoperforate the glass. And as you see, it's of course contactless. There's no material removal, so no necessity for exhaust system or whatever. And now we move the piece, the sheet further on the belt to the separation gantry. And now here the separation laser follows the same contour again, and this leads then to the separation of the parts. If you do a job change, it's essentially all you have to, you load the new file, the new recipe in the system, so it's all done by software. There's no need to additional setup of the tool, like when you do braking with a brake ball that you need a different template or something like that. That's not necessary here. I come now to important benefits of laser beam cutting. First of it is we have a fairly high edge strength. So typically between 80 and 100 megapascals. And with our enhanced nanoperforation, that's an improved version. Essentially, we push that by additional 30 to up to 50%. So we can land typically at 150 megapascal with our enhanced nanoperforation. Compared to that, of course, the results with mechanical cone break and other methods are not as good. And also with cone break, you have, of course, more difference between the top surface and the rear surface, because the top surface you scribe with a scribe wheel before. And with the water jet abrasive, or with the abrasive water jet, of course, it's even worse. That means if edge strength is important, you need to grind much more to get to the acceptable values. It's also interesting that they zoom into the edge surface, and then very interesting here the lower two pictures where we removed just a little bit of material. This was done by etching, and what you see here, when you remove only 5 microns of the material, you don't see, or practically you don't have any subsurface damage anymore. And this is essentially one of the reasons, if not even the main reason, for the high edge strength. So it's not only the good chipping. And this looks, of course, different with cone break, where we have the cutting marks from the scribe wheel, or then even worse, of course, with the surface cut with a water jet. Similar differences when we look at chipping. Front and rear are pretty similar, so our own results are even better. There's virtually very little difference between the front and the bottom or the rear surface. But all these results are essentially from a very extensive comparative study by the Vilnius Technical University in Lithuania, together with some institutes there. They did really a nice study and also published it. And for the sake of consistency, also the results with laser are taken from that paper. That means, of course, if chipping is a criterion, then with the conventional methods, it's required to do grinding, or at least more grinding than with a laser cut edge. Worth to mention is also that with a laser cut edge, typically, and with a low chipping, if you are putting then the glass in a tempering furnace, there's no post-process necessary of the laser cut edge. You do it directly from laser cutting, and you can do the tempering. As far as I know, that's not possible. Essentially, with mechanical cone break, you will have then breakage. That's why people are typically do first some grinding or even some chamfering there. Another aspect is, of course, as already mentioned, there's no mechanical contact. It's a dry and clean process, so there's also no wear and tear, and so we have a consistently same high performance with our laser cutting, and that's again different than with mechanical cone break. You of course have some degradation of the tool. That means also some change of the cutting quality over production time, and it's even more so than with water jet cutting, where you have to frequently replace the water jet nozzle. For really 24/7 operation, typically our customers have often then a really fully automated laser processing system. These are now real-world numbers. The two graphs show essentially the yield loss of two systems in two production lines. They produce the same parts. And you see that in average, you have around 1% yield loss. That means 99% yield. And typically feed rates in our systems currently up to 1 meter per second. That compares roughly also to mechanical cone brake. But of course, water jet cutting or diamond saw are slower and even slower when you go to larger material thicknesses. So that brings us now to the first use case, cutting off side windows in the automotive area. First of all, why is it of increasing interest, side windows? In conjunction with the increased adoption of electric vehicles, there's also now more demand for laminated side lights. Also, it's not legally required yet. Legally required is only the laminate for the windshield, for the safety glass, but side shields typically is tempered monosheet. But why is it so interesting for electric vehicles? The reason is with the laminate you have a better acoustic damping, and especially when they use so-called acoustic PVB, that the acoustic damping is even better. And that's so interesting for electric vehicles where we don't have the noise of the combustion engine anymore. So the ambient noise is relatively more dominant. So that's why they are interested then essentially to insulate the cabin better against all the ambient noises. And doing this now with a hybrid laminate, for example with soda lime glass and aluminosilicate, brings an additional advantages like higher durability and also additionally the weight reduction. Now here the use case, this is a drawing of a side shield. It's a little bit distorted, generalized drawing. Here done with Gorilla Glass, 1.1 millimeter thick. And on this given mother sheet size, when we do the cutting with laser, we can tightly nest those freeform designs so that we get 8 parts out of a mother sheet with a high material utilization. If it is done with conventional cone brake, where they cut first the rectangles and then the near net shape with the XYZ cutter, you get only 6 parts out of such a mother sheet with a lower material utilization. This translates in in this case to 57% less glass waste. And if now done, for example, with Gorilla Glass, which has a higher price tag, you have then with one laser tool glass cost savings of $2.5 million per year. These 1.4 million parts, this correspond essentially to the tech time of such an industrial laser tool, where we run the processes in parallel, where we have then about 13 seconds tech time per part. To achieve the same throughput, one would require several cutters and CNC grinders to get really to the same net shape and the same edge quality as with laser cut, plus additional corresponding floor space, plus additional labor, plus the consumables and washing. So using a laser, in this case, saves then essentially material cost, and at the same time you avoid all these additional costs in operating expenses. We come now to the next use case in architectural glass. First, let me to bridge that. Historically, we typically cut glasses with thickness 2 or 3 millimeter, and we wanted to cut thicker glass. We had essentially do multi-pass cutting. That means we just changed the focus height, the additional pass, to fully nanoperforate again the glass thickness of the material. So meanwhile, there are good or industrial lasers available with higher pulse powers and pulse energies. And with that, then we scaled our technology. That means also adapting the beam shaping design to that we now can cut thick glass up to 10 millimeter, or in the lab even 12 millimeter, but up to 10 millimeter in a single pass. That means we are as fast as with thin glass. We also achieve then this up to 1 meter speed per second. And also the nice thing here, we have the same high uniformity, the same low subsurface damage as with thinner glass or with low power version. Of course, when we developed this, we had, for example, one application in mind to cut smart window structures. So in the lab, we did quite some experience with also stack cutting, different thickness, different air gaps. And below you see then a microscope picture of a real smart window structure. And when you go to thicker glass, you can also do it with cone brake, of course. But Then with higher force or with a higher pressure of the cutting wheel, you have then increased chipping again, and you may need to change the cutting wheel and work with other fluids, whatever. And similar limitations then or other limitations than with water jet cutting, so it's not as versatile as with the laser. And also impressive is essentially then this microscope picture of this 8mm thick piece. You see again, it's very homogeneous. And because of that, you can decide whether the laser comes really from the top or from which side. You can also break it essentially in both directions. And you can also break it mechanically. So there's quite some flexibility when it comes to complex structures. These now application example for smart windows. Smart windows, we talk here about the switchable glass, where we essentially have two ITO-electrodes in between the active material. Can be electrochromic or liquid crystal base or suspended particles. You apply the voltage, then you can switch it between transparent and opaque, or then in also different shades. And here with a laser, now with this high or thick glass capability, with a high power version, we can cut the full stack in a single pass. And as well, then we can cut this, what we call the half cut or the step cut, to make the ITO electrode accessible for the electrical contacting. And we can flip it and do the other part so that both ITO electrodes are accessible for the contacting. And we optimize that process so that you really just cut the upper part with minimal damage to the ITO layer. So there's practically don't impair the sheet conductivity. And also you see, or in tests, that the required long-term stability is maintained of the ITO electrode. If you would do this in a conventional way with mechanical cone break, you would do it first, cut the mother sheet to the individual sizes, and afterwards you would do all the coating and layer deposition, of course, which is something which is not that nice. And that's then a big advantage of laser, that you really can do all this prefabrication on the mother sheet level, and then you can cut the individual sizes of the big part. And that's of course streamlines the process, and it essentially means also then cost savings in the production. I come now briefly to the environmental impact. Already yesterday evening in the opening ceremony, we have heard a lot about sustainability and climate goals. So it was also there mentioned. Maybe first the graph in the upper left corner. The good news is that the CO2 footprint or the CO2 emission per ton of produced glass has steadily decreased. But I think the biggest part of that is simply because the shift away from coal. And also that, of course, the energy mix for electricity generation also has shifted away from fossil fuels. So it's not that much the efficiency increase in the industry itself. But important, we know we have this Europe's Green New Deal with a goal to be climate neutral by 2050. And in conjunction with that, there are quite a few regulations in the works. One of them I've heard is the digital product passport, which will cover essentially all the processing steps from the raw material till the final product, essentially the full chain, and will be likely rolled out first in industries like furnitures, like textiles, but sooner or later it can be expected that it will be applied also to other industries. And so for that purpose here, just exemplary calculation of the environmental benefit of the example we have seen. We have seen the savings in glass material with the assumption that, for example, now all 66 million new cars per year are equipped with such windows. You would have savings of 45,000 tons of glass per year. And then you can calculate with the energy mix essentially the savings in CO2 in the different steps. And of course, with increasing, in future, I think there will be more and more price tag to that also, whether it be about CO2 taxes or CO2 emission certificates, so that there's some costs associated with that, or then cost savings. So I come now to the summary. We have seen glass cut or laser cutting is a precise and versatile process. Because it's so precise, we can do the net shape cutting, and that allows us to the tight nesting, and that allows us to get to the high material utilization. And also we can cut these complex structures and value-added glass, like in the smart windows example. We have this very high quality. We have this process cleanliness, which is interesting as soon as you have some whatever sensitive coating or so, which hydrophilic, hydro whatever, you can still process that. And all that together leads then to a low total cost or low cost of per part. It enables novel design features and even new functionalities. And you have the reduction of the environmental footprint. Just maybe one more word to the low cost. Of course, the capital invest of the laser is higher than with the conventional technologies. So please don't, in your companies, don't let your procurement people decide on which technology you use. Really, please look at all implications of the different technologies. Take into account the operation expenses, or then the savings operation expenses, which goes on really into the cost per part. What should be the decisive factor? This is not abstract theory, so there are our field-proven platforms available. Of course, we also offer smaller tools for pilot series and so forth, but these are the typical Gen 6 and Gen 8 tool, which are used for the use cases you have seen. These are platforms that can be configured to your specific needs. For example, low, mid, or high power laser for thick glass, our nanoPerforation or enhanced nanoPerforation. So there are essentially defined options so that we can decide or that we can choose together with you the best machine configuration. And what I've not shown here, because it would be too much for one talk, we introduced also our cutting platforms to cut 3D shaped glass. So the smaller one was the first one. With this 3D processing volume, the typical target is, for example, 3D shaped cover glass for automotive interior displays. For example, nicely S-shaped cover glass for center stack display. And this is now the latest release, the larger version of that. With that large processing volume, you can simply put larger part in that. For example, a complete panoramic sunroofs and cut features which are difficult to do with conventional methods again. So that was it. Thank you very much for your attention. And now I'm happy to take your questions.